Share screen. Okay. So, I guess we shouldn't start at the start. Let's start where we were. So we were speaking about the issues of reasoning and some of the reasoning tasks that we can have. And we mentioned the fact that when we want to do reasoning, when we want to perform entailment, for example, we can reduce entailment to unsatisfiability. And then we mentioned, okay, so we can reduce entailment to unsatisfiability, but that doesn't really solve the problem because we still have to figure out how to implement satisfiability. So in terms of how do we test unsatisfiability then, depending on all the features of our ontology language, as we spoke about in class 4, it may not be possible, okay? And why is this the case? Because essentially there are certain things that computer programs, algorithms cannot do, that machines cannot do. So there's this notion of undecidability that some of you may have seen before. And this is an example of a Java program, right? So what we have here is essentially, we have some input, which is a number, okay, an integer. And then we call this function here, and then we just print out some information. So what does this function do? It receives a number, an integer. Okay, it prints out the number, and then it says, if it's 1, return. Okay, so finish. So the program finishes, it halts. We say it halts when n equals 1. If it's even, okay, if we divide by 2 and get a remainder of 0, then we call the same function again, dividing by 2. Okay, so for example, if we have 6, we'll call the function again with 3. However, if it's odd, then we multiply it by 3 and add 1. Okay, slightly strange operation, right? But a relatively straightforward program. So if we have, for example, an input of 6, then what happens? Well, 6 is even, so we divide it by 2, so we get 3. If we have 3, we were going to call this method again with 3. This time it's odd, so we will call the method again, this time with 10. 5, 16, and then we see once we reach a power of 2, it might be evident what will happen. Once we reach a power of 2, we will divide by 2, divide by 2, divide by 2 until we get to 1, and the program halts. Okay, so what's interesting about this program is that it's not clear if this Java program terminates on all possible positive inputs. Not just here, this is coded with an integer. So I'm not talking just about the integers, but all possible natural numbers, let's say positive natural numbers. So would this program terminate? Nobody knows, right? So is there some number that somehow will loop, for example, that somehow you will reach some number and then reach some other number in a for loop? Nobody knows. So this is an unsolved problem in mathematics, the Collat's conjecture, it's called, whether or not this program will halt, right? So if we knew that this program terminates or does not terminate on all natural numbers, the problem would be solved. So essentially, there's this idea that if we could say whether or not this program stops or halts on all possible inputs, then we would have solved this problem. We haven't. Okay. So the halting problem is this idea of that we're given an input, which is a program and an input to that program. So for example, the program might be Collat's, and the input to that program might be the number 6,473. Essentially, the halting problem then should return true if the program halts on that input, or false otherwise. Okay, so essentially we'll say this program is going to halt or not on this input. So this problem is undecidable. So it means that essentially a general algorithm to solve the halting problem does not exist that will itself halt, right? That will itself always return an answer. Okay. So essentially what this means is that it will not halt for all program input pairs. Okay. Um, Although it might halt for some program input pairs. For example, if the input to the halting problem is collapse as the program and the input is 6, then we could just simply run collapse on 6 and it will terminate. However, if we pass collapse, if we try the same strategy, we pass collapse, and we pass this magical number that the program doesn't terminate for. If we try the same thing of just running collapse on the input, if it takes forever, then that strategy of the halting problem would also take forever. Okay. Okay. So I don't want to get into proving the halting problem. It's a classical result from computer science, a very old result, due to Turing. So, but what actually happens? What's the rough idea? The rough idea is that if we had a program, this halting program, that could tell us if any other program halted on any other input or not, and always return an answer. That halting program, we could call it, right? So it's a program, so we can have another program that calls it, okay? So what we can do is create a mischievous program that calls the halting program on itself, okay? And if the halting problem says this program here is going to halt, then this program will continue forever. It will just contradict what the halting problem says about itself. Right? Whereas if the halting problem says that it won't halt, then this program here returns. So essentially it asks the halting problem, hey, halting problem, what am I going to do? And the halting problem says, you're going to terminate. And then I say, okay, I'm going to run forever. So this creates a paradox. It seems like a cheap trick, but it creates this paradoxical situation. This impossibility. So we can have this program that can somehow call a halting problem and contradict and do exactly the opposite of what it says. So the real proof is slightly more complex because there's some subtleties in how a program can pass itself as an input into the halting problem, but that's the rough idea, right? There's a program that somehow asks the halting problem what's going to happen and then contradicts, does exactly the opposite of what the halting problem says, and that creates this contradiction. Okay? And of course, the program that calls a halting program is valid because the halting program is a valid program, and this program is just calling it as a sub-procedure. So it creates an impossible situation with two valid programs. So we must conclude then that this halting procedure cannot exist, because if it did, it would give rise to these impossible situations. So as an example of decidability, undecidability, we can consider a problem which is the consecutive ones in pi. So we're given as input a natural number, and our program output should return true if pi contains n consecutive ones, and false otherwise. Okay. So the question is this problem decidable or undecidable? Any ideas? So pi continues, right? It's a transcendental number. It continues arbitrarily. Of course, we should expect, for example, sequences of 2 ones, sequences of 3 ones, sequences of 4 ones, and so forth. So, is this problem decidable or undecidable? Well, it might seem undecidable, but we have to remember, the question is there a program, does there exist a program that halts with the correct answer for all n? So essentially it might seem undecidable, but in fact, if we think about it, what if we knew the maximum sequence of consecutive ones in pi? So this means, what if somebody told us the most times that consecutive ones appear in pi is 42, right? For example, this is not really known. It's not known what that number is, right? It's not known if there's a finite number. So what if we knew the maximum sequence of consecutive ones in pi? if we knew the maximum sequence of consecutive ones in pi and we had to implement this program, it would become super easy, right? One of the easiest programs we'd ever have to implement, right? Which would be essentially, we take the value of max, which is the maximum sequence of consecutive ones in pi. We check to see if n is less than or equal to max. We return true, otherwise we return false. Okay. So therefore, we must conclude that the problem is decidable, right? So what we don't know is what this program is because we don't know this value, but we know that there exists a program. Okay, so we conclude that this problem is decidable. Okay, so hopefully that makes sense. This is kind of to warm up to the idea of decidability and undecidability. Similarly, if we have the collapse halting problem, we have it as input none. So we just have some blank input when we don't consider, or we can pass something and ignore it if we like. The output would be true if the collapse program halts in all inputs or false otherwise. Okay. Is this problem decidable or undecidable? Does there exist a program that will always return the same answer or the correct answer and halt with the correct answer? Well, we have two options. We have a program that can just return true or a program that can just return false. So in fact, even though we don't know which program is correct, we can say that it must be decidable because either program 1 solves the problem or program 2 solves the problem. We just don't know which. Okay. So this is to emphasize again that the halting problem is undecidable in the general case, which means for all programs and inputs. Okay, so if the input were rather a number and the output were whether or not the collapse program is going to halt or not on that input, then we would have a problem. The difference here is that we're just asking a true-false question, right, with no input. So halting problem is undecidable in the general case. As an example of a more interesting and visual example of an undecidable problem, there's many problems have been found to be undecidable. The domino tiling problem. It's a quite intuitive problem. So what we have is a set of dominoes like D, and essentially we have a set of patterns like this, and we can have as many actual tiles for a pattern as we want. So we could have an essentially we could say infinite number of tiles with this pattern, right? Or an infinite number of tiles with this pattern. What we'd like to do is tile the plane. So what do I mean by the plane? Start in one corner here. Okay, so we assume we start in a corner, and then we want to be able to tile in all positive directions of the plane. Okay. So so it's not just that we want to tile the plane, we want to say whether or not it's possible even to decide the plane. So how can we choose? How can we say that? How can we decide whether or not these tiles can tile the plane? If we had a pattern which was just red, 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 that would be very easy, right? We could just say, yeah, that tiles the plane, no problem. If we had something like red and red here and blue here, no problem, we can tile the plane. But we see that in the general case, how would we implement a program to say yes or no, right? So we accept this finite set of patterns here. We accept a set of patterns as input, and as output, we want to say true if we can tile the plane with those patterns, or false otherwise. So if you think about this and how you might try to implement it, you can quickly realize that actually it's in some cases it's trivial, but in other cases it's not clear what the general algorithm would be, right? So in fact, this problem is this problem decidable or undecidable? It's in fact undecidable. Okay, so we can't have a program that will accept this set of dominoes here and say whether or not it can tile the plane. Okay, how do we know that it's undecidable? How do we know that there cannot, no matter how excellent a programmer somebody is, that they won't be able to to solve this problem or create a program in Java or Python or whatever to solve this problem. And because it has been shown that if we could solve the tiling problem, then we could actually use that program to solve the halting problem. Okay, so we can, what we would say, reduce this problem to an instance of this problem. We can convert an instance of the halting problem into an instance of the tiling problem, which perhaps does not seem so intuitive at first, but essentially we can consider somehow these tiles to be transitions, and there are certain rules between which tiles we can navigate in a certain direction. So okay, I'm not gonna. I don't understand the proof. I haven't seen it in detail, but that roughly is maybe some of the intuition. So we can represent somehow operations in what would be called a Turing machine as part of the tiling problem. So given this fact, okay, we assume this fact to be true. This fact has been proven. Is the domino tiling problem decidable or undecidable now? Well, if it were decidable, and if we could reduce this to this, then this would be decidable as well, right? So essentially it means that since we know this is not decidable, it must imply that this is not decidable either. Okay. So what do I mean by reduce? Essentially, somehow there's an implementation of the halting function that produces a set of tiles for this problem here, and then calls this method here with has tiling. Okay, so it converts the program and the input into some sort of tiling question, asks the tiling question, and gets an answer back. So this is proven to be possible. So then the point being that since this is undecidable, there must be some problem here. This must be undecidable. Okay, so here's the argument, which is why we can conclude that the tiling problem is undecidable as a result of this fact here. Okay, so what about OWL? Why am I talking about tiles and colors and decidability and undecidability? So if we consider this again as our symbol for entailment of ontologies in OWL, what we'll discuss in the next class is the fact that we can solve this problem, we can express this problem using the ontology features that we saw in the class on last week. So this means that we can actually represent the details of this problem as an ontology entailment question, and it's not very difficult to do. So we'll discuss the details of that the next time. So what does it mean? We can reduce a question of does D have an infinite tiling to a question of does our ontology O entail O prime. So how can we do this? How can we encode this? We will talk about that in the next class, and then we'll talk about different types of reasoning algorithms that we can apply. So what's interesting about this is that we were somehow showing that there is a general result that knowledge is undecidable. So somehow machines are not capable of doing any sort of entailment or deduction that we might like to do, or we might express. So essentially there is a limit to the computability of knowledge, to being able to give knowledge A and ask is knowledge B true as a result, right? And this actually relates directly to the halting problem. The original statement of the halting problem was a similar statement of being able to prove things in terms of algorithms, mathematical results, which is known to not be possible. So we'll talk about the reduction, and then we'll talk about different algorithms for doing reasoning and what kinds of, okay, if it's undecidable, we can't, there's no general program that can solve our problem completely. What are the options, right? So what are the other things we can do? So we'll talk about that in the next class, and we'll talk about different forms of reasoning with respect to that somehow try to avoid this problem of undecidability. Questions? Any questions or comments or? A fun little example, if you want to think about it a bit more, is writing a program to solve this. So I've already given you the spoiler that you can write a program to do it. Certainly, you can write a program to brute force exhaustively try something. It may terminate on some inputs, but it won't terminate on all inputs. Okay, so it's an interesting sort of problem. Also, if you get asked this in an interview, you can know that this is a trick question. Okay, so if there's no questions or comments, okay, so we stop the share so we can start to think about the lab. So I'm going to, 1 second. I'm just gonna open, I see Jaime has kindly uploaded the PDF. So, okay, and I'm gonna share. So essentially the introduction, as an introduction, it's going to be very similar to the overall way you addressed Lab 4. Lab 4 was with respect to sorry, trying to find the enunciado here. So Lab 4 is with respect to property axioms. So this lab, this time we're going to focus on class axioms. Okay. So with respect to this title, I think you'll have to ask Jaime what this is a reference to. I'm not sure what the knuckles part is. So we have some data that's again about Irish mythological figures, and this time with respect, it describes weapons that they wield, and some other information about tribes and so forth. So this time what you will need to do is to define class axioms. So class definitions and class axioms to solve these problems. So the first thing to do would be to copy and paste the data into the left side of RDF playground. So you're going to use the same tool. And then on the right side, you'll need to provide some definitions to solve essentially the entailments that are given. So in this case, we describe a little bit more detail about what kinds of things we want you to define, because the definitions are a little bit more complex than they have been previously. So here's an example of something that's a super complex definition that we could do now, right, in Turtle syntax. So let's have a look at the example. It defines a class. This is a class here, okay? So, and it defines a second class here, and it says that the first class is a subclass of the second class, right? So anything that is in this class here must be in this class here. Anything that's an instance of the first class must be an instance of the second class. What does the first class describe? What's all this stuff in here? It describes a class that's the intersection of a list of other classes. It describes a class that's the intersection of a DCC student and either a master's student or a PhD student, right? So we intersect student, DCC student, with the union of master's and PhD students. Essentially, we can think of this intuitively as postgraduate DCC students. Okay, so this class here defines the notion of a postgraduate DCC student based on these other classes: DCC student, master's student, and PhD student. Okay. What does it say? It says that essentially this class that we've defined we haven't named it as such, but we could call it the postgrad DCC students, is a subclass of those that have some values from, okay, that take a value from the class intersection of professor and DCC staff, that take a value from this class here, which is intersecting professor and DCC staff, which we could consider to be DCC professor, okay? So it has some DCC professor on the property supervisor. Okay, so it says that essentially this is the class of things that have a DCC professor as a supervisor. Okay, so what we say essentially is that all postgraduate DCC students have a DCC professor as a supervisor. Okay. So what it does not state that all of the supervisors of a student are of a DCC postgraduate student are DCC professors. They might have professors from other departments or from other universities. Nor does it say, for example, that all of the students of a DCC professor are DCC postgraduate students, right? What it says is simply that postgraduate DCC students, every postgraduate DCC student has at least one supervisor that is a DCC professor. This is a particularly complex example, so you're not going to jump straight into defining these sorts of things. But it gives you an idea that you can sort of nest these definitions like we have here. So here, instead of, here we nest this concept of, here we nest this concept of a union, right? So we define the intersection of a union, right? Or here we define some values from on an intersection class. So this way we can define rather complex axioms, right? The axiom here is subclass of. Okay. So the two types of axioms you have to consider are subclass of or equivalent class. Do you want to say that all A are B, which is just subclass of? Or do you want to say all A are B and all B are A? Right? Do you want to have this sort of two-way relationship between the classes? So, okay, so we have 7 questions, and you'll have to address each one by one. Okay, so they start a bit simpler, and then they get a little bit more complex. Okay, I don't think there's one as complicated, quite as complicated as this one. So these are referring to the class axioms. In 1 or 2 parts, you might also use a property axiom. So you might define subproperty of, or inverse of, or is a transitive property, or something like that. Yeah, so otherwise the lab is quite similar to what we saw previously in the previous lab. So with that, any questions or doubts? Okay, so we can pass over to the Discord in that case. So the enunciado is published in the in cursos. So see you in Discord. I'm going to stop.